So I thought about just going through the self-learning notes that I sent you. So we will go through them for 1 hour and just try to solve together an example or two. And I think there was a really nice idea that you offered that maybe we'll begin each question that you have 5 to 10 minutes just to try yourself to think about how to start, and not only me lecturing you, because then you really just won't fully understand. So we can start with this question that I think I already solved before, but we can start with it because you can repeat it. So we can start with this, or we can start something new. What do you prefer? Do you prefer to do this or a new one? Who says this one? And who said a new one? Okay, let's start with this one, and we won't do the Fanon factor MCV. We will do only the autocorrelation and the hazard function. So we have the neurons in the ductitis excipitation, the nucleus of the mountain troll fire, which fire pairs of spikes of 5 milliseconds apart every 100 milliseconds. So you need to draw the autocorrelation and the hazard functions of the neuron, and in the range of 0 to 250. Go. And you can do it in pairs, so you can speak with each other. Pairs, threes. These are 2 lines, just note. Each time it's 2 lines. 5 milliseconds between, so 0, 5, 100, 105, 200, 205.
So then it's always here it looks like the first five is on the 0.
On the 0, yes.
Is it always like that? Should I assume that
Yes.
when
Yes.
we draw the
If
turn
you,
starts at 0?
yeah, we often assume that there is 1 and 0.
Yeah. No.
But you need the expectation of the
Spike count.
yes.
And you said that it's spike count in time, so no need to divide by the time duration, only just to count the number of spikes.
And that's expectation.
Yes.
Okay.
But we are now, please note, we are not doing the Fanon factor in CV, only the autocorrelation and the hazard.
But still, the margin will be calculated.
Yes.
What kind of
Yeah. So that's not what I mean. I think if you look at one, maybe one sentence.
But I think we have to come to 259 seconds.
Oh, okay.
In the question, right? So we stop here, I think.
Yeah.
So I think the range was still not. When we then move on to but just when we say 0 to 200 milliseconds, it refers to the time lapse or to, okay.
It's very confusing. Most of students are confused with it. So it's of the shifting, not of the time resolution.
It's about 1 minutes. And not
I've
today.
seen those, I think, each one of 1,000 seconds. By
The 205,
Same number, so the same variable, so the same.
Yes.
But I think we don't have to look at. Yeah, but I mean, the requirements, I was looking at in this. One, because the other one.
we'll have 2 more minutes.
I guess, yeah, what I'm trying to, for me, I'm trying to say that two, very, like, the way you think about it. Two types of, in the public. On, 95, so.
We are just. And we are starting with one that I showed before, I remember, class, right? So.
Yes.
The best group.
Right, because yes, I'm looking at this one area. Yes, because each variable is. You can imagine that it's not green, going up in passing a lot by trying to inside of them. This one doesn't have. It is separated the green and the red, and you have half green, half red. Okay, so you're saying, we don't have to.
Okay, let's see the solution. I think it was very, very good, and I highly recommend it. Maybe after the reinforcement, you will go on, okay? But now I just want to remind you the solution, because I stopped because there might be a possibility that some of you are a bit stuck, and just waiting and looking at the blank sheets cannot help you. So we'll just go on now, and in a minute I want to show you another kind of exercise. That I don't know, I think that in very high percentage there will be something like this in the quiz, because I would write something like this in the quiz. So this one is it's a bit easier, because in this one we can really count the PDF, right, of the spikes of the eye size. We have only 2 eye size, right? We have 5 and 95. So therefore we can conclude that we have 50% for the 5 and 50% for the 95. So the CDF looks like this, and if you divide the PDF by the survival, Then you get this hazard, right? So for this hazard, what does that mean? That if I came to 5 milliseconds, what probability is it that I saw a spike? So it's half the cases, so it's half, right? But then let's say that there was no spike. Where will be the next one? So we can say that for sure it will be at 95, okay? Yes.
I get analytically how you get there, but with the equation we have, I don't understand. The number, when I plug in numbers, just
Yeah.
computationally, I get 0.25 and two,
Right.
or non.
So please note that in the CDF, we put the value prior to the current time. Okay, so we won't have this infinity.
Okay,
Okay, so for example, here, let's write the PDF. So the PDF is half for 5 and half for 95. And the CDF is 0 when it's for ISI less than 5, half for 5 to 95, and from 9 and for bigger than 95, it's 1, right? So the survival, which is 1 minus the CDF, is just complementary. So it's 1, half, 0, and less than 5, 5 to 95, and bigger than 95, okay? And now when I do the PDF over the 1 minus the CDF, okay, so when I do it for the 5, so I take the half here, and I divide it not by this half, okay, but by the value before, okay? This is what this epsilon here means. It means that we take the value 1 before. So the value 1 before is 1. Therefore, this one equals half.
But it is. Isn't it one?
It's 3.
Sorry, wasn't it 1 minus CDF?
Right, but in the CDF, we don't take the exact number here at this current time, but the one just right before, okay? And this is due to quantization of the data. Also, when you do the project, don't take the current number, take the one week before, okay? And here, so this is 5, and then in 95, again, I'll do the PDF. The PDF is, now it's half, right? Over the one before 95, so it's over half. So this one equals to 1. Okay?
But if we take the PDF for the value before 5,
Yeah,
then we would have 1 minus 1 in the denominator, right?
where?
No, it's
the whole thing is 1
1
minus
minus
CDF.
okay, got it, thank you.
I use this. Okay? Great. And again, please think about it as if I didn't see a spike so far, what is the probability to see a spike now? Okay? This is the right way to understand the hazard function. And spikes are dangerous, therefore it is hazard. Okay, now when I compute the autocorrelation, I need to count all possible pairs of spikes. So we know that we have spikes at 5 and 95. But then we need to also count spikes which are not adjacent to each other. So we have the one at 100 milliseconds, right? And the one at 105 and 110, and so on. So I'm just writing to myself all possibilities until the shift of 250. Okay? And the last one is, of course, 205. And then when I do this shift, is it clear why is it for half of them the 595 and for all of them it's the 100? Yeah,
It's usually.
Okay.
Shift, you have the alignment.
yeah, exactly. So you can calculate the autocorrelation in two ways. The first one is to say the following. We have here spikes at 0, 5, 100, 105, 200, 205. Now, the first way is to count all possible pairs, okay? So I say to myself, how many pairs do I have which are 5 milliseconds apart? So half of them, right? So for 5 milliseconds, it is half of the case. And for 95 milliseconds, it's the same. Now let's look at the following one. For 100 milliseconds, for how many spikes do I have 100 milliseconds apart? So I have the one at 0 and 100, and another one at 5 and 105. So for each spike, I will have one possibility that there will be a next one within 100 milliseconds. So if I have a spike, let's say I have a nice meeting and I was just sitting here, and when I saw a spike, I opened my clock. And then I wait for 100 milliseconds. What is the probability that I will see another spike? 100%, exactly. So for this reason, this one equals 1.
So you think if our like whole cycle wasn't 600 milliseconds, but was only 205, we would have 4 out of 6.
Yeah, so in these questions, okay, you commonly don't count. It is true that in class, I showed you that I count, but I count within a specific period. And then I take from the count to probability, not by normalizing, but by understanding the pattern. Okay? So it's not, I just did it like this because when we look at this pattern, we can see already the pattern over here. We don't need the full spike frame. Was that clear? Okay. Yes.
Rate for autocorrelation was a problem on last quiz. Could you use this example and show going from probability autocorrelation to rate autocorrelation?
Yes, within 1 minute, okay? So now let's look at the next possible latency between two spikes. What is the next one? Great. Why? Great. And in how many cases is it like this? Half. Because what will happen if the meeting got this spike? You won't see one at 110, right? He was waiting for 100 milliseconds and there was no spike over here. So this happens only if I am in the beginning of a pair, right? So this is again half. And then the next one is 195, right? And this one happens only for the second one in the pair with the one at the next pair. Okay, so this is again half. Okay, so this is one way to calculate it. It's just like counting and then writing it out of all the possible probabilities. Yes.
But if it only happens for the second spike
Yeah.
with the fifth spike, right? And we're looking at one period. Kind of like, if we look at one period, it means we look up to 100, right? Because that's when we complete
Yeah.
the
Yeah.
period. But then, how do I, like, if I'm stopping at 100 and I add 195, how do I know, how do I count?
So I will probably just take longer than double the number that I've asked. But here, okay, you can probably the right thing to do is that if you're at about 250, plot at least until 600 or so, okay? Do you understand my answer, Edwin? So go on. But the idea in autocorrelation is that we are not interested in what is the sample that we have. We are interested in the pattern that we have. We are assuming that our sample is infinite. So we are not really interested in counting the numbers. We do it only when it's really complicated, okay? We are more interested in the probabilities themselves.
Because I just added up for the first three, and I'm like, okay, if I'm skipping every other one, it means it's half.
Yeah, yeah. Because you always say, okay, for 195, I have to take the last one here and the first one from not the second puzzle, but the one after. So you need to explain it to yourself by the mathematical rule of this sequence. Okay?
Yeah, I'm going to use that idea for no matter which time. So should we look at, I don't know, the window size, let's say the 4 first slides, and then count within them how many
Yes.
slides have this interval?
Yes, this is one possibility to do it. But let's say that you just need really, really long. Okay, and now what I want to show you is that another way to solve autocorrelation problem is by copying your spike train and shifting it. Okay, so let's say that I shifted my spike train with take the 100. So I shifted it. If I take the 100, I take it left, okay? So I have here 0, 5, and here 100, 105, and here 200 and 205, and 300 and 305. So now when I shifted it, mentally shifted it, I can see that each spike has a spike above it. So therefore, the probability for 100 is 1. Let's take the 195, okay? So let's shift it by 195. And this is kind of the thing that we can do in the draft. So I'll shift it even more. So if I shift by 195, then I first start with, if I shift by 195, this is irrelevant for you. So let's first look at this one, right? Because around 195, I'll have a relation here. So the 200 will move above the 5. And the 205 will be later. And here, there will be the 300 and the 300, sorry, it's here, of course, the 300 will be here, and 305 will be here. Here, 400, and here, 405. So when I shift it mentally, one of the things that is happening is that now I can really see visually what spike has a spike above it. And I can see now that it's only for half of the spike that they have one above it.
3 out of 6.
For example, yes. Okay, was that clear? Yeah.
So what I understand is that we have to look just at the pattern as if the signal was infinite, but then
Yes.
we have to do the autocorrelation function. We just have to look for this window, which is
Yeah. So the number of shifts that you will do, the maximum shifts you will do is 250. Okay. Now, the next thing that Austin just asked me is how do you calculate the firing rate? Okay. So I will do it as the following. How many spikes do I have in 1 second? If I have 2 every 100 milliseconds, then how many spikes do I have in 1 second? So to solve the question of how do I normalize it to rate, this is the probability. I want to normalize it to rate, so I ask myself, how many spikes are there in 1 second? So 20, right, because I have 2 every 100 milliseconds, then I have 20 spikes. So it's 20 spikes per second. Therefore, I need to take this 20 and multiply it by the probability. Okay, and in a minute I will explain what does that mean. So here, in the 5, it's 20 spikes, right? So this will be 10, and here we have 10, and here 20, 10, 10. Okay, and what does that mean? So let's say, take for example, the 195 millisecond shift time lag. So that means that if I shift the spike frame, what is the rate that the spikes here meet here? Okay. So they meet a rate of 1 spike every 100 milliseconds, right? And 1 spike every 100 milliseconds is 10 spikes per second. Okay? So this is just another way to normalize it, but the easiest way is to multiply the number of spikes by the probabilities.
So
Yeah.
so that means that 10 spikes will align
Yes,
this shift.
yes, within 1 second. Exactly.
And what's the interpretation of this? What can we?
Okay, so autocorrelation and cross correlation is a way to see what do you say? To see patterns in the neurons. So let's say, for example, and for many neurons in the brain, it is like this, that a neuron is not interested in the number of spikes going in, but rather in the rhythm. So let's say you have a neuron here that is the doublet one, and there is one here that this one will be excited only if it has 60 milliseconds apart between 2 spikes. So what is the probability that this one will fire? It's 0, right? Because 60 milliseconds, this one responds to 2 spikes 60 milliseconds apart. So what is the probability that this one will fire? 0. Do you understand why? No. Okay. This one, after each spike, after each spike, he waits for 60 milliseconds, and if there is another spike, then it fires. Otherwise, it won't fire. Okay? So what is the probability that this neuron will fire given this spike frame? 0, right? And if it's not 60, if it's 100 milliseconds, it's 1. And if it's 95 milliseconds, great. Okay. And this idea is, there is also a theoretical framework called Sim-Fire chain, that it shows that neurons are not interested in the firing rate, but rather in the rhythm of spikings and in the correlation between spikes. And this is something that Moshe Abeles, that will come also this Tuesday to the neurophysiology seminar, so please come. Is a very great theoretical in neuroscience, and he proved few times the Sim-Fire chain rule, that that in many cases the brain works by the correlations and not by the firing rate themselves. And he also established this center. So I think I really love to hear it, speak about it. But cross correlation and autocorrelation are some of the basics of this theory. Okay? And they are highly used. For example, I heard a very nice lecture of someone called Hagai Bergman, who just won the Israel Award for Science. And he developed the deep brain stimulation. Do you know what is that? The people with Parkinson, they have like a kind of a pacemaker in the basal ganglia that it reduces the symptoms of Parkinson and allows people that cannot behave naturally at all. It just reduces all the symptoms. And he discovered the rhythms and the fact that there is this beta oscillation only by cross correlation. So it was really nice to hear that something like this is very practical. Okay. Now let's do something which is a bit harder. And we have the following rate function of a non-homogeneous Poisson process neuron. Okay, so this neuron fires in a rate of 100 spikes per second. If, do you know what does mod mean? Mod is the reminiscent. If you take the time and divide it by 50, so for example, if you have 60 divided by 50, it's 10. Right, so so what are the times here? It will be less than 25.
0.5.
Right, exactly. Okay, so this is what this means. And it will be 0 otherwise. Okay, so first of all, you have here also a draw for this neuron. So look at the cycle of this neuron. You have a cycle within every 50 milliseconds, right? And in this cycle, half of it is with a rate of 100 spikes per second, and half of it is with 0. Okay? Is that clear, the neuron itself? How it fluctuates? Great. So, the neuron is sampled at 1000 hertz, recorded for 20 seconds, which is really infinite time. And now we need to draw here it's the spike count autocorrelation function of the neurons. Yes.
For 350, the mod will be 0.
From 300 to 325, it is 100. From 326 to 340, from 325 to 349, it's 0.
But isn't it 0 also on 350?
At 350,
Isn't
when you divide it by 50, you don't have any reminiscent, right? So the reminiscent is 0. So 0 is smaller than 25. So in 350 specifically, there is a firing rate of 100 milliseconds. And I know this is a very, very hard question. So there is a way to solve it. And I want you to first try yourself for 5 minutes, okay? Yes.
So the autocorrelation, should it be on a given window?
Do it for 200. I said yes. I'll check for a second. No, this won't help us. You can even do it for 200. 100, sorry. Yes.
So when we say 100 milliseconds in autocorrelation, we mean we stop there.
The shift can be even 100, yes. Do it for 200, okay? The shift, yes. Side leg. Is it equal to 25? No, so it should be 0. So again, I'll just write here, so it will be organized. So in 0 to 25, it's 100. In 25 to 49, it's 0. 50 to 74, it's 100. 75 to 99, it's 0.
So here we don't know the probability, right?
This is the rate.
Okay.
Yeah, it's an autocorrelation for spike count.
So between 0 and. Well, we have 24 survives.
No, it's, think about it again. If it would be a flat line, a homogeneous Poisson error, how many spikes would you have for 1 second? 100, yes. But here, it's not a flat line. Yes. So you have 50 spikes per second. They apply to your.
No. That's the one that we are in. So you said, if we have one like this.
Would you like to join?
What's that?
I can stay with you. Because I think one thing is, again, I know that when you look at it, really clarifying that you're kind of. Okay, I'm like, right, so there is no formula. To how it so
You have the first one divided by, you have the. Divided by 40. So wait, let me know who's the exact divided. So if you have 100, okay, start like this.
For the first.
And you don't have anything here, you don't have anything here, you don't have anything here, it's 60 seconds. Right, okay. Now, you have 50 seconds.
So let's say, let's start.
Because we have periods. Every 15.
Sorry, 25 seconds.
So then, you refer to it.
Yeah. Yeah. With what,
You would, if it was a straight line, you would have,
right.
you would have.
So here,
If we have like two.
this is what
Oh, yeah, yes, but then.
yeah, how many spikes do we have? We have 100, right? Yeah.
Show that.
We have
it's-
1 second, therefore. Yeah, range of spike that I would.
Yeah.
I think, but. Right? We don't have to do that. How much time we have what numbers? And how do we therefore, what is the value? Oh, I like.
Now I would transfer to understand.
Because that's where-
We divide this into.
Because that's what, that middle.
That's the open coordinate.
That would be 100 meters, second, by everyone, like, that would be
So.
Because you could change 25 or 35, that would just be another big with a potential. Yes. It's not.
Then I do. So that's because
This is the number of steps, so that's going all right, so one second, we have, now the next thing we're going to find, right? Start and share. And up, so. Okay.
But actually 17.
So try to do it. I'll have 2 more minutes. Yeah, of course. You're. I was not sure I could say it then. And
No, I didn't. It was just, I thought if you were to continue, then I'm saying stop. It's gonna be too up to 0, a stagnation. So basically, from the. Some.
Yeah.
But like, so. When I think about the plan, I was like, okay, let me look at this. Like, let me check.
But I don't know the idea is really good for them, you know.
Oh, yeah, as it says. You can go back.
Yeah, but the basic idea explains the rational idea.
Like, what I mean, if it's not us, right, and nobody like that either. It's, gives one time that's not.
Right.
Which means, but only for half.
Right. Right, way to go.
Yeah. So then go, if you hate that as just see, the wording.
we're not
that I
looking at
said,
the-
it means
we're not looking at
that
that.
if it. Then the total.
So if this was did not work, it's.
But then what happens is, it says like, at 0, you have 1,
Yeah.
and like, you have 1, but then 30, 40, you don't, and then 50, 60.
Yeah,
Okay.
But
So it's like,
what we get-
instead of being average, things are like 60. You know, like, how many spikes do they expect? Yeah, no.
Okay. One last minute, so just try to finish what you're at, and I'll show the how to solve.
Because if we do it up to 50. Because they're what's the spike on? So you're not even stopping 29.4, right? What do you want to do with the? You already know. From 25 until 50, you already know the balance. Or you want rates, how many, 100 will not be. So what I want to know is the number of spikes in this 25. So you do, so there's a rate of 100 not. The rate of.
Okay,
No.
let's go, because I hear you had a terrifically great progress. You did it really, really good. I know that you don't feel like it, but I heard here really, really good conversation among all of you, and you were in the right direction, so it was really good. Okay, so First of all, let's read it together. So we have 220 seconds. So we have a period of 50 units, let's say 50 milliseconds, okay? I don't know why I wrote 50 units. Therefore, we can solve the problem for one period and multiply it by 400, right? So I don't need to look at all of the 20 seconds. I can look only at 50 seconds and look what is going over there. And this is the number of periods along the sample. And in each period, we have two parts. First one of Poisson neuron in the first 25 milliseconds and 0 in the last 25 milliseconds. So, okay. So let's start with the easiest one, which is what is the number of spikes along all of the recording, okay? So the number of spikes is the autocorrelation at time lag 0, right? Do you understand why? Because if we think about the idea of shifting, I just copy the same spike file and I put it above the other one. And then this is the number of spikes across all of my recording. Yes, okay. So for each period, so for the 25 first beams that the firing rate is 100 spikes per second, we have an average of 2.5 spikes, right? Therefore, during the full recording, we have.
You cannot multiply by 400 because it's that it would mean that you have a rate of 100 hertz for the whole, but it's sorry, I couldn't.
It's okay, it's okay. Another way to solve it is to say, if it was a Poisson neuron, a full one, and it was 100 spikes per second, how many spikes would I have in 20 seconds? So I have 20 seconds multiplied by 100, right? So it's 2,000. But I have only half of the recording is 100 spikes per second, right? So I have half of 2,000, which is again 1,000, okay? 400 is the number of periods that I have. So I go back here, I have this again and again and again and again, 400 times. So I can calculate all my calculation only for this part, and then multiply it every time by 400. Yes.
Did you really have 25, 400 times? You have it 16 times in order to have 400.
It's for 20 seconds, right?
Okay.
So in each second, I have 5 like this. Right? Did I say something right?
Yeah.
1 minute. No, I have to, in each second, 50, I have 200 like this. I have 20 like this, each second, right? So if I have 20 seconds, it's 400. Do you understand? Sorry, I got confused myself. Okay. So now the next spin, oh, and by the way, I wanted to tell you that already when you look at this kind of a Poisson neuron, the answer should lead you to something like autocorrelation of a oscillatory neuron. It should look a bit fluctuating, and we'll see in a minute why. Okay. So now we want to compute what happens when I'm not at 0, okay? When the time lag does not equal 0. So we can see what is the number of beams left for calculation for tau equals 1. Sorry. So what I'm doing now is I started my mental shift. And when I mentally shift these cell beams, I shift them, each time I will shift it by a specific number, and I'll think to myself how the cell beams are meeting the other part. So I'll show you an illustration from another question. about it, not this one, this one. That's rather this one, okay? So you see? So how do I solve it? I shift it mentally, and then I look at the tips. What kind of, what do they meet? Do they meet a trough? Do they meet a peak? Is it in any way, for example, this is a harder question that it's kind of a combination, okay? So in some cases they meet this, and in some cases they meet this. We'll do it maybe in the next recitation, or you'll try to solve it yourself. But I mentally start to shift it. Now, when I shift, exactly. So I can start either by shifting it, so I will have full overlap. Okay? And when will this happen, that I will have a full overlap? 0 and 25, they will be, okay, let's, if it will be 25, they will be fully non-overlapping. Okay? So this is this one, and this one looks like this, right? This is 25 millisecond shift. But if I shift by 50 milliseconds, then I will have a full overlap. This with this, okay? Great.
And you don't consider the fact that you're missing one, right?
No, no need.
It's just 100%.
Yes.
Okay.
How much is the last shift?
50. Okay, so you know, let's solve it like this. I like this way better than what is written here. This is after I finish the full non-overlap and then the full overlap, then I go into the what happens when it's a partial overlap. So let's first start with the full and the partial. So if I have, let's start with the full. So if I have a full overlap, then what is the probability of the spike here to make a spike here? So I have here a probability, there are 2.5 spikes here, right? And 2.5 spikes here. So there is a probability of 1 minute. 0.05, do you understand why? Why? Multiplied by 0.05. Why? A probability to see here. Oh, 1 minute. Is it 0.05 or 0.01? 0.001. Okay. Let's see. Okay. What is the probability that in this specific 1 millisecond, I have a spike? It's 0.01, right? Why? Why? Because I have here 100 spikes per second. So for each millisecond, the probability for a spike is 0.01, right? And this is the same for this one.
Okay.
Okay? So the probability that a spike here will meet a spike here is 0.01 multiplied by 0.01. And how many beams like this do I have? Here, only at this 2. I have 25. So this is doubled by 25. Okay? So I look at the beam here and at a beam here, and I double the probabilities and double it by the number of beams, right? Because I will count it for each beam It's this plus this one plus this one.
And then should we multiply by 400 because it's
Right, and all of this, since we have 400 SOTI. So this is being multiplied because this is count by 400 units like this. Okay?
So how does 100, I'm sorry, how does 100 divide, yeah, how does 100 divided by 1,000 become 0.01?
Is it
Are
100?
we not counting?
Maybe, no, maybe, should it
One
be?
divided by 100, it's 100 divided by,
But it's,
it's 100 divided by 1,000, right?
Right, so the probability for 100 divided by 1,000, yes, so you're right, I'm sorry. There were too many zeros over here, you're right. I'm sorry.
We're just converting spikes per millisecond.
Yes,
Sorry.
yes, I'm writing them as a probability instead of a firing rate, because firing rate, yeah, it represents the probability.
So this
Okay.
is probability.
Yes,
How will we find it?
so I'm looking at the bit of one millisecond. And I'm asking myself, what is the probability that there is a spike here and another spike here? So the probability of a spike here is 0.1.
What one?
It's 100 divided by 1,000.
Sometimes it's between
Spike per second, this is the rate, divided by 1,000, yes. Because you look at a specific 1 millisecond.
Yeah, it's just to convert the units, right?
Yes,
If you expect 100 as 1 second, and you expect 0.1 and then.
exactly. Thank you. Yes,
Why did the X one was?
where?
It's like 0.1 times 0.1.
Yes, because you need
Yeah, times 25 of them, times 100.
400.
Becomes 400.
Okay,
But you see, times 25, that's something.
exactly.
But then why in the beginning, why did we say that the rate was 50?
The rate,
The total rate, because it's 100,
It's-
it's a flat line.
yeah, because it's only half of the duration that you have 100.
But here we considered it for each 25 millisecond bit, it's 100 hertz. Rate.
Yes. So the probability to have at 1 millisecond is 0.1. It doesn't matter what happens to the rest.
Okay.
Okay?
Big world, 50.
No, 50 is just when we use kind of the average to compute the number of total spikes, so we were using this, right?
Okay.
So leave it out. We are now asking the question, what is the probability of 1 millisecond to have a spike in the circuit? Okay?
Did you know where to have the?
Yes.
spikes per second?
Yes. So now what we need to do, so we have it for this one, so we said that this is 0.1 multiplied by 0.1, multiplied by 25, and then multiplied by 400. This is the count of every 50 milliseconds, right? Because every 50 milliseconds, there is a sawtooth meeting another sawtooth, fully overlapping. Now let's see what happens at the 25. This is easier. At the 25, the sawtooth are non-overlapping, therefore each spike here won't meet the spike here, right? Because this is 0. So the probability here for every 25 plus 50 millisecond, you can write here n because this is the full cycle, is 0, right? Because in 50 it will be this, but in 75 it will be this. So this is why I wrote it as 25 plus a cycle of 50. Yes. So it's not only 25, it's like every It's 25 plus 50, 25, 75, 125, and so on.
And can we just do QC of number, and that means the lag, when we write it in the exam, can we just do QC of a number?
Yeah,
That's fine.
I like to write like this, 25 plus the second.
It is written as N.
And, yes. And it's just a number. Okay, so now we have the full overlapping and the non-overlapping. Now we need to start dealing with the partial overlapping, okay? So let's start by, I'll use the black. So let's shift just by 1 millisecond. Okay? Now this one is getting wider. Okay, I don't really need to draw everything because it is enough to look here. So what happens when I shift only 1? How many milliseconds from here are overlapping with a millisecond from here? 24. So now, what? Because you have here one that is overlapping with this one. So you take one less. So it depends on where you're looking at. You're saying, I'm looking at the spike here in relation to spike here. So you have 24 spikes here, and they could be overlapped with 24. So now you have again, what is the probability of a spike within this thing? So this is 0.1, right? And the probability here is again 0.1. So it is 0.1 multiplied by 0.1, and this time you multiply by 24. Not by 25. And how many cycles like this you have? You have 4. Okay? So now you understood that each time I need to take 1 off until I get to 25. And then when I'm going on, I still have between 25 and 26. What happens between 25 and 25 and 50? I can look, for example, at the 26, right? And in the 26, we understand why it will look the same. There will be still overlapping of only 24. Excuse me?
For 26, we
Yeah.
have lots of 1.
Overlapping of 1, sorry. Yes, exactly. Because now I need to climb back, okay? So I understand that each time I'm linearly taking 1 possible bin, and after 25, I'm taking back 1 possible bin. So I try to write it mathematically, okay? And let's see if we understand. So for tau equals 1, we have an overlap of 24 bins, 24 milliseconds. For tau equals 2, we have 23 bins left. Similarly, from tau equals 26, we have an increase, so that in tau 26, we have overlap of 1 bins. In 27, 2 bins. Is that clear so far? Therefore, for each tau, we have the absolute of 25 minus tau. Okay, you don't really have to write it, but this is just another way to express this linear decrease and linear increase. Okay? In every period for calculation. Now we can calculate the probability of spike at each bin, which is 100 over the full duration, which is 20. Okay, anyhow, I tried to remember why the 20,000. 20,000 is the number of milliseconds in the full sampling, right? So I probably just, yeah, so I took it across all the samples, but you can still leave it as we did. It is the same. It equals the same because 0.1 multiplied by 0.1 is exactly this.
Why is it divided by half?
So you have only in half of the sample. But it should have been 0.1 as we did before.
Like
Okay?
the result should be open.
Yeah, it is equal the same. It's just another way to calculate it. So when this 1,000 is the number of beams, and we have this fire and bright only at half of them, yes. Therefore, for each tau, the autocorrelation function will be 25 minus tau multiplied by 0.01 multiplied by 400. Okay? So the autocorrelation should look like this. I'm sorry, I just cropped it from the row. Okay? So it really looks bad. But here at 0, it is 1,000, and here at 50, it is 100. Okay, because if you do it over there, this calculation is 100. Okay? And at 25, it's 0, and it should look linear. Okay? And this is exactly how autocorrelation of, yeah, it's really, it's cute. Okay, let's say for that.
So we didn't use this formula in the exam when we see that there's a bursting behavior, or like not bursting, like oscillatory behavior.
Yes,
We just do
exactly.
QC, okay, modulo of.
Yes,
Okay.
but in a minute I'll show you, maybe try to do it today after you understood the way to do it. So, and now they ask to normalize to the firing rate. So we are normalizing, we have 1,000 spikes and the size of bill is 1 millisecond. So the autocorrelation just really looks the same because these are canceling each other. Exactly. Yes. Yes.
Yeah, so, no,
Here?
yeah, here, the 0 point, it's supposed to be, no, the calculation 100 divided by DI, it's supposed to be 0.01, right?
0
That's
point
what the calculation is.
01. Yes, so this is what is
Okay.
written here.
Okay.
Yes.
And in the autocorrelation graph,
Yes.
I understand, you know, the peak, the big peak, I understand the 0 over 0 in the 25 and 75, etc. But it's supposed to be between, for example, between minus 75 and minus 24, 25. It's supposed to be,
Linear triangles.
so, just.
Yeah, this is an absolute function, so it looks like this.
So,
Okay.
we're not supposed to work like this.
Yes.
It should be triangle.
I'm sorry, I just again draw it by row, so it looks really. I try to make it look more realistic. Okay. And you see, for example, when I did the course, this was my solution. It was not in an exam, it was in a project, but it was we had like this kind of a project in class, and I got full points. Okay, so although the drawing is really ugly, when you really show the understanding, the mathematical understanding, you will have full points. Okay, so if you want to try, so.
How do you know? Sorry. Do you see it? Or should?
I said like really briefly that now we need to normalize it to rate. So normalize it is divided by the number of spikes, right? And then dividing by the size of the beam, which is 1 millisecond, i.e. 10 by -3 of second. So they cancel and you're left with dividing by 1, so they are equal. Yes, so when you want to go from the count to the rate, you need to divide by the full number of spikes that you have in the sample, which is 1,000. This is the probability. And then divide it again by the size of the beam in second.
Why do we have, one period is 50 milliseconds, right?
One period is 50 milliseconds, yes.
Why do we have 1,000 spikes per if the rate for 25 is 2.5,
Yes,
why does it become? a
you have
1,000?
400 cycles,
Yes,
so it's 1,000 spikes.
so it's not per period, it's not per 50 milliseconds, it's per
No.
50 times 400?
Yes, you have to multiply it by this. In count, it is dependent on the size of the sampling.
Okay, thank you.
So for example, if it would have been here written that you have 50 second duration, I need to count it by 50, by the number of periods in 50 seconds, which is about 1,000.
Okay.
Yes,
Should be divided by 100, not 10. To the power of 29.
it should be,
I mean,
Yeah.
it's weird that 1,000 divided by 10 to the power of -3.
no, 10 to the 3, I meant to add, not minus, sorry. I'm sorry for all the things here, but again, it's a full answer, even with these calculation problems, it was. I just really want to show you that it's okay to do mistakes and just stop being so hysterical about it. So, this is another nice question, but I don't know if we'll have the time to do it. But I want to show you, based on the question that we just did, if you want to try to solve a very similar one. So this one has a neuron, which is regular. And this one alternates between ISIs of 100 and 200, okay? So he has a spike at 100, 300, 400, 600, 700, 900. Is that clear so far? Okay. And then there is neuron B. And this is a Poisson neuron excited by neuron A. Every spike of neuron A leads to an increase in neuron B firing rate from baseline of 10 spikes per second to 20 spikes per second. So this is harder, first of all, because the baseline is not zero. This one, you can say that the baseline was 0. So now they are not 0. It's 10 and 20. And besides, it's not just an oscillating one, right? So you need to sketch the autocorrelation functions of neuron B and the range of plus minus 500 milliseconds and normalize it to rate. And I think another question here was, what is the cross correlation from A to B and from B to A, or something like that, and we can solve it. So the first thing is to understand how to draw the neuron. So you can see here, since there is a spike in neuron A for 100 at 100 milliseconds, there will be a response of 104 for neuron B, and it will be for 20 milliseconds. So I start by drawing it. And now you need to think about what is a full overlapping, what is a non-overlapping, and what is partial. And there are a few kinds of partial overlapping here. For example, that there is an overlap between this one and this one, but there is no overlap of this one with the other one, right? Because an overlap from this one to this one is shifting by 200 milliseconds, right? Shifting left, sorry. So you need this to meet this. And when you shift this by 200 milliseconds, it means no overlapping. So this is not a full overlapping. So a full overlapping is only by 500. When you take all of this, right? By 400. When you take this to this and this to this. 400, 300, 300, sorry. Just look at the numbers. Okay, so you start by finding the full overlap, the no overlap, and the partial overlaps. In this case, there will be also a partial overlap that has full overlap and non-overlap, right? And then in between it goes linearly, as we just demonstrated. Okay, so this is a nice question to try after you sleep And you submit the second project or part of it. Okay, see you at Wednesday. And we have also next week, I don't know if next week we'll do more autocorrelation and cross correlation. I feel that the subject is much more clear and now you can just try to solve yourself. So maybe next week I'll speak to Sophie about how to get ready to the. Great, you're welcome.
From those last one we did, because it seems to use the method that got all of us in trouble.
The what? Yeah.
It seems to use the method that got us all in trouble on the quiz. I say all, the people who got 500. So I understand QP, if you divide it by 1,000,
Yes,
this example, you get
the probability, yeah.
Previously, in your other example, you then took that times the average rate,
Yes.
20 spikes per second.
Mhm.
Here, you're multiplying, and what we did previously to get wrong was multiply it by the sampling rates. Divided by the sampling.
Okay,
Divided by 1,000, you got 500.
yes,
Here, you're dividing by the sampling rate, another thing.
yeah, because this is the size of the bin.
Yeah, I'm saying what we did was in our quiz, we multiplied or divided by the size of the bin 107.
Yes.
Got us 500, which was way too big.
Hmm,
Here, instead of dividing by 10 to the power of -3, shouldn't you multiply by 1,000
yes,
spikes divided by 20 seconds?
to get into seconds.
That's what you did for this version. The unit, like the 5 and 100 interspections.
Mhm. I'm trying to think about another way of phrasing, because what we can say is to say that our average firing rate is 50 spikes per second, right? And then I'm thinking how to get from the count to the probability. So I'm thinking if it is only to. No, I understand your question, it's okay. So is it just dividing by 1,000? No, it's not divided by 1,000. No, okay. Look, the probability, for example, for full overlapping.
Yeah.
Was here, and then we multiplied it by 400, which is the number, so the probability will just be without it, right?
It'd be dividing by 1,000 spikes.
Why?
Why? To get the probability of one spike. So we have, there's about, on average, 100 spikes that will overlap for each 50. That's what we found. Or we wanted, right?
Yes.
And there's so that's 100 spikes out of 1,000 spikes. Have that. Like, we expect that.
Yeah,
So you divide by 1,000 spikes, you get your probabilities for each time. which is
yeah, but I
also
think that here we directly calculate the probability of two spikes to meet each other. Do you understand the difference? I understand what you're saying, but I'm wondering to myself, maybe, I'm thinking about the formula of
So if we want,
dividing the sound into the number of spikes.
yeah, that's what we also, that's the formula we use.
Yeah, right.
Right, or the count
But,
divided by that.
Now I'm thinking about that. And then I'm saying to myself, like I showed you here, we calculated the probability and then we multiplied it by the rate.
Yes,
So the right thing to do is that we calculate the probability of spikes meeting each other here, right? And this is, it relates to the number of cycles that we have. This is just the full probability.
Okay.
So now if I want to see what is correct, I need to multiply it by the frequency.
Uh-huh.
And what number is it? I think this is not 100 seconds, right? 105 per second.
150 is 12.5.
So based on what I said here, the maximum should not be 100, but rather 12.25, right?
Yeah.
And this is different from what we have here, that the peak is 100. So this makes me wonder about the normalizations. So if you can please email me, I had some doubts anyhow about the normalizations that are written.
Yeah.
If you can email me and I'll double check it with in the book, okay?
Okay.
Because I am very highly sure that this is the way to calculate.
Okay. Yeah. I think it's just we're getting stuck in the equations that we were given. Because we were given 3 equations. And it's basically like
Yeah.
Q is simplified. QP is your count
Divided by.
divided by.
So I think that is depending on the number of spikes.
Yeah. You mean QR is equal to this divided by N times our bin size.
Maybe you
Yes.
just have to like brush him
But
with a line.
Here,
Yeah,
I will.
when
and
you
I
do-
think this is last time.
I will.
yeah, this is the one that we got that gives you 500 for this. When you show it here, it makes a lot more sense that it's 1.5. That was great. I also say, I also say I did calculate in the online Zoom, it said like, oh, what if it's like 1? It actually increases the longer you go. So like if you have 1 second, 100, or it was 100, so 500 per second.
Yes.
If you have 100 all together and then like for 1 second, and then 5 seconds more of 500 minutes,
Yes.
you get a fire rate of 2.6. And it kind of supports the bigger big defense. But it's uniform, it's around.
Yeah, it was again, and I signed mine. And there was a correlation.
So, yeah.
So if you have to 1.6 and you divide it.
Well, that's what I'm saying. So you pointed out that if you go, you have 100, 100, 500. And then you have
And then I'll write you
Just
a message and how.
1. Yeah. That looks fine, but actually you don't have a half. So I didn't win. So, okay. Another-
Right.
You do it for one number of 500, and then 500. You get two. And then I went further and I did 1 second of this, and even more.
No, we need more, because you need to all be on 1, 2, 3.
Yeah, that's what I'm saying. So
Right, so this is
Today, they will, like, remove the money. We go to September.
Or-
And they take, they keep the deposit, and then they pay us back.
5.
From-
If you do it for this,
Three things we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's really like a 5 years.
the overall rate is still 3.
Yes.
But if you calculate the autocorrelation for 500 milliseconds
Oh,
over this, you get closer to 2.
So they will send. you-
And if you extend this to 1
right,
second
because they
period,
have this one and this one, no.
yeah. And then if you go for 1 second of this, you have just in these, you have 5 plus then all of the.
Wait a second.
Okay.
I might have potential is plus this
With, my Israel
right?
adopt, but either she.
What is the time? Yeah, so instead of saying just up, we just add another one, right? Might be like in the other correlation, time mark every 500. Right, so what we saying is with a half of the event, plus another one during this process, right?
For the fact, this is the minimal impact.
Yeah.
Further, yes, then add more effective. So and then you add more spikes. You have a spike here, here, and here. And so then as you stack these over 500, over a 500 period, what you end up with is divided up to 2 seconds with 12 seconds extra to make sure I have equal amounts of intervals of each. And it trended for 3 spikes for the 5 minutes.
Wow.
Because I have to highlight my other one.
Yeah. And all still within the same passage.
Yes.
But
Okay.
still, none of that is 500. So that's why. I
So
was-
ask me for now and double check it because I base my explanation on this presentation, but I'm wondering maybe it looks like there is a right. Yes.
This seems what it is.
Yes,
This is what we did here,
yes.
and that kind of makes sense.
Not zero and the average. Yes, yes, yes. I really have to go.
Okay.
Yeah.
Yeah,
Like, rent. Okay.